Well, good morning, everyone. Today we're going to go over sections 4.4, concavity and the second derivative test. And you'll notice that it's a little bit different of a format. I don't have access to the classroom anymore, so I'm going to experiment with different things. So today we're just going to kind of go through the notes a little bit, the ones that you've got posted online. So again, we'll just kind of go over some examples of it, and I'm going to kind of break the videos down into sections for this one just to see how it goes. So I think I'm going to do just like I'm going to cover the intro on one video, and then we'll do an example or two in another one just to kind of piece it out a little bit, and so the videos aren't quite as long. All right, so we've already seen how the derivative can help us define local extrema and even determine if that point will lead to a local max or a local min. And that was using the first derivative test and so on and so forth. So with this information, we can determine the basic shape of the function. However, for some function, that's not enough. So for example, if we knew that the first derivative was positive, which implies f is, from the last section, we know that if the derivative is positive, f is increasing. So what could we draw for f? So we kind of have two options of what we could do. We could draw something that's going like this, because that's clearly increasing, and the derivative is still positive. Or we could draw something that went like this, because that's also increasing and the derivative is still positive. So we kind of have two options for this. Well, now let's kind of flip it around. So now let's say that suppose the derivative is negative, which implies that the function is decreasing. So what could we draw for f? Well, again, we're going to have two options. We could do something like this. So the function is decreasing from left to right, and the derivatives are all negative. Or something like that. So we still have the two options, and we don't really know which one it is, just to say that, hey, the derivative is negative. So if we actually knew how the function curved around, or the concavity of f, we would know which option to actually choose. We would know which of the two we actually have. So the concavity occurs in two ways. You can be concave up and concave down. So if we go back to what we drew earlier, like this graph for here, when the derivative was increasing, this one, that one's concave up, and this one over here would be concave down. So if you think of like a parabola, a positive parabola looks like this, that would be concave up, and a negative parabola this way would be concave down. And you can always just kind of half it on each side, but they're still concave up and still concave down. So in this next example, draw two graphs that are always concave up. Well, we just kind of drew one, so it kind of gave that one away. So just a regular old parabola. Or, like I said before, you can kind of half the parabola and do something like either one of these, like this one or this one. And it doesn't matter which one it is, because they're both always concave up. Do you remember what kind of function that is? That is an exponential curve. All right, so anyway, example 2, draw a graph that is concave up and then switches to concave down. So concave up, and then it's got to switch to concave down. So let's do one that's concave up, and then we're going to connect it to something that's concave down. And we can shift this up a little bit if we wanted to. You can even throw in a vertical asymptote. So So concave up, and then it switches to concave down. So it doesn't say it had to be continuous either. Okay, so how do we find this concavity? Well, fortunately, there's a test for it. So let f be a function whose second derivative exists on an open interval I. So if the second derivative is positive, then the graph of f is concave up. And if the second derivative is negative, then f will be concave down. So almost like the test for when the derivative was positive, it told us the function was increasing. It's kind of the same thing with this. It's just now you're using the second derivative and we associate it with concavity. So in that example 3, the one where we drew the graph where concavity switched, either this one or this one, it switched in concavity. So there must be a point where this happens, and it's called an inflection point. So if concavity changes and the point's actually there, like it actually exists, then we have an inflection point. So how do we find them? Well, it's really similar to how we found critical numbers. So if we know it's an inflection point of f, then either the second derivative, and that's important, it's the second derivative, not the first. So the second derivative is 0, or the second derivative is undefined. Okay, so that's the intro video to inflection points and concavity. So the next video we'll go ahead and do some examples, and you can see how it works.